Hi, I'm Earl,
I am Angelica.
And I am Dale.
and today we'll be explaining and simulating one CPU scheduling policy and one replacement policy.
Yes, that's completely right. But first, we will explain the process of the policy, and then the logic behind the policy, and then afterwards, we will be running some simulations with the program.
So without further ado, our first CPU scheduling policy is the shortest job next, or the SJN scheduling policy. This algorithm is a greedy algorithm, meaning that it selects the best possible option available at the current moment. Basically, the algorithm works by selecting a process in the waiting queue with the smallest execution time to be executed next. With this, SJN has the advantage of having a minimum average waiting time among all scheduling algorithms, as it prioritizes processes that can be completed with the minimum amount of time. However, it may cause starvation for the longer processes if shorter processes keep on coming. This problem can be solved by using the concept of aging. SGN could be preemptive or non-preemptive, but for this presentation, we selected the non-preemptive SGN, meaning the processes cannot be interrupted once they are being processed.
So, the algorithm will be as simple as this one. First is that of all the processes that arrived in the waiting queue, they will be rearranged according to their burst time. So, what about the processes that will arrive in different times? Of course, the CPU will then resort the given processes and will again rearrange them based on their burst time, ascending order.
Moving on with the logic of the program, we have here a Python program for SJN scheduling policy coming from CPP secrets. Here we can see a class SJF containing 5 methods, which I will be discussing each, starting with the process data method, which accepts inputs to enter the information about our incoming jobs, or in this program they call it process. This method asks for the process or job ID, the arrival time of that process, and its burst time. The inputs for one process are put inside a list called temporary, with an additional data set to 0, which will be used to indicate whether the process is already been executed or not. And that list is appended to another list called process data, creating a 2D array or list of the incoming processes or jobs. After getting the inputs, this method calls the next method, which is called the scheduling process. This initially creates a list for the start times and exit times of the processes, which will be used later in the computation of the waiting time and turnaround time. We start with an S time of 0, in which we initially sort the data according to index 1 of the process data list, which is the arrival time of each process. After which, we have this two-dimensional for loop. The first for loop, I, is to cycle for each of the process we have in our list, while the inside for loop J is to cycle through every process and identify if they are already at the ready queue and if they are not yet processed. This portion of the data checks if the process has already arrived and it appends it to the ready queue. Else, if the process is still not executed but also still hasn't arrived, it will be appended to the normal queue, which is the waiting list. Once all the processes has been distributed to the ready queue and the normal queue, we proceed in this if condition that if the ready queue has something in it, it will be resorted according to the index 2 of the data list we have, which is according to burst time. After which, we are ready to put the processes in the queue. To remember the time where each process started, the current S time is appended in the start time list we created earlier. And then the S time will be updated with a new time, which is just the current time added with the burst time of the process that is being queued. This will also be the exit time of the first process queued, which will be appended in the exit time list we created earlier. This for loop K is just used to identify the index of the current process being queued, and this K will be used to update the index tree of that particular process to 1, meaning that it has already been executed. After which, the exit time of that process is also appended to its list as the index 4. However, if the ready queue is empty, we start to get a process from the normal queue, which is the next process to arrive. Here it just updates the current time with the index 1 or arrival time of the next process, and then, same process, append to the start time list, compute for the exit time, append to the exit time list, search for the index of the process, use this K to update the status of the process index 3 to switch it to executed, and append the exit time to the index 4 of the process. These processes will be applied to every process in the list with this for loop I right here. After which, two methods will be called, which are the calculate turnaround time and calculate waiting time methods, which will provide a value to the t time and w time variables. After which, the print data method will be called to print the results. As for the calculate turnaround time method, it creates an initial turnaround time counter. And in this for loop, it will cycle through each process in the list, calculating its turnaround time by subtracting the exit time appended in index 4 to the arrival time placed at index 1. This computed value will be added to the total turnaround time counter and will be appended to the current process as index 5, which will be used later in calculating the waiting time. After going through all the processes, the average turnaround time will be computed by dividing the total turnaround time counter with the number of processes in the list, which would then be returned as a value once the method is called. As for the calculate waiting time method, same process to the turnaround time, but it utilizes the index 5 or the turnaround time we just appended, subtracted with the burst time at index 2. Same process in which the total waiting time will be incremented with the calculated waiting time. The waiting time will be appended as index 6, and the average waiting time will be computed and be returned once the method is called. This print data method, on the other hand, just prints all the data we calculated through these for loops that cycles through every process in the list. Finally is the main method, which is the starting point of the program, which initially asks the user how many processes are there in the sequence. At this point, let's try a simulation of the program, and let's use the example we had a while ago. So let me just speed up entering these values. And as you can see, it produces the table where each process has been solved, with the same turnaround time and waiting times.
So for the next, our chosen replacement policy algorithm is the first in, first out page replacement policy. This algorithm is the simplest among all page replacement algorithms, in which it merely selects the oldest page in the memory to be replaced by the incoming page.
So, the algorithm is really simple. Goes like this. The first one, who comes first, will get the memory first. Of course, every time the queue changes, it will be marked as a page fault. So, what about page replacements? How are you going to replace the pages? Of course, since this is a first in, first out algorithm, this means that the one who came in first will be the one who will go out first. This only applies if the queue is full. Remember that. For this algorithm, think about it as a line. The first in the line is going to be the one that gets removed if there's a new page incoming or a new process incoming. However, if the page is already in the queue, then there will be no changes made. Remember that this unchanged queue will be marked as a page head. This process will then apply to all the pages until all of them or all the processes are done.
So for the program of the first in first out page replacement algorithm, we have here a program from prepinsta.com illustrating the entire process. So let's explain the code bit by bit. In this first line, we have imported a predefined package queue and store it in an object called queue with the small letters. Here we have a page faults method, which calculates the entire paging process. This line is just the headings of the table that will be created later. Initially, this method creates a set, which will be the slots for each frame, and after which we create a new instance of queue called queue with a capital Q, which will store the incoming pages and remember the order of their entry, since a set cannot do that for it is an unordered list. We also initially put a page fault counter to count the page faults as we go through. Here we cycle through each of the incoming pages, and if the set S still has a frame that is unoccupied, the next incoming page from the stream will be added to the set or it occupies a frame. This increments the page fault counter as a change in the queue was made. The incoming page is also put into the queue to remember its entry. But else, if the set is full or already occupied with pages, first we need to check if the incoming page is not yet in the set, which is done here. If the incoming is not yet in the set, meaning we need to replace a page, we remove the first one in the queue or index 0, since this is first in first out, and index 0 is the first that came into the queue. Next is we remove it in the frame by removing it from the set, and after which the incoming page will be added in the back of the set and the page fault will increment as there is a change in the queue. However, if the incoming page is already in the set, then nothing will happen. This part of the code prints the current incoming page and the current pages occupying the frames. This will all be applied to all the incoming pages with the use of this for loop. After which, the total page faults will be returned once the method is called. As we go on with the main or execution part of the program, here we define the list of incoming pages, the number of pages in the list, and the number of frames the queue can accommodate. This page faults variable calls for the page faults method, which would then print the entire process and return the number of page faults. Lastly, this computes the number of hits by subtracting the number of page faults to the number of total pages, and then both of the numbers are printed. So let's try and simulate an example. Given the example we used in the explanation of Dale a while ago, let me define the data in this list. Upon execution, the program will produce a vertical table of the current page with the current queue containing the frames, which, as you can see, similar to the table of our example. This also computes for the page faults and hits of our given list of pages as seen in the bottom of the output. So that is all for this video. Again, we are Earl, Angelica, and Dale, and this concludes our Opsys course. Thank you and have a good day.